All right, live session number 4.
Okay, are we live?
We are.
Okay, take 1. There is no second take, but the floor is open for your questions.
Okay, the first question is from our friend Julian. Hi, Julian. Low mass stars have titanium oxide in their spectra. Where does this come from? It seems like an odd molecule for stars to have.
Yeah, interesting and a good question. And it was surprising when people first observed this. Basically what happens as you look at very cool low mass stars, dwarfs basically, the very coolest stars we can find, the M dwarfs, K dwarfs, even L and M, there are even cooler stars that have been discovered in the last few decades. And you look in the red part of their spectra are chopped up by troughs, absorption troughs. Not narrow lines, but they're broad, and they typically are associated with molecules when you see kind of broad troughs like that, rotational transitions of molecules. So when these were first observed, some decades ago now, they were mysterious. It was not clear why the stars should be chopped up by absorption like that. And it turns out that when these lines were identified, these absorption bands were identified, they matched lab chemical spectra, lab spectra of titanium oxide, TiO basically, a single titanium atom matched or bonded to a single oxygen atom. And as Julian, you imply, indeed, that seems surprising because oxygen is fairly abundant, but titanium is a fairly rare element, down at 1 part in 10 billion in cosmic abundance. And so really what happens is that titanium oxide is a very stable, naturally forming molecule on the Earth. I mean, it does exist on the Earth, even though titanium is fairly rare on the Earth. And what happens is in the outer cool envelope of stars, the relatively rare titanium atoms bond very easily and readily at temperatures of 1,000 or 1,500 Kelvin with oxygen. So almost all the titanium that's available, even though it's very rare, is going to bond to oxygen and form this TiO molecule. And then it's about a matter of atomic physics or molecular physics. It turns out that these TiO molecules have a very strong and resonant absorption due to their rotation, oscillation, and vibration. And so they create these very deep spectral signatures. So, in the detection of molecules and atoms in stellar spectra, it's not simply a matter of abundance, it's also a matter of the atomic physics of how readily the molecules are formed, given the basic ingredients. And it's also a matter of the atomic physics of how strong those absorption transitions are, which can really imprint them powerfully in the spectrum. In the case of titanium oxide, both things are going in the favor of detecting them. So even though titanium is a rare element, in these cool outer regions, its signature is so strong that you can detect it anyway. And it's an example of a larger phenomenon where stellar spectroscopy is extremely efficient and sensitive at finding rare species. So we found technetium, we found transuranic elements in stellar spectra, I mean, things that are actually phenomenally rare, hundreds or thousands of times rarer than titanium. So stellar spectroscopy is an extraordinarily powerful technique for diagnosing rare elements and finding them in stellar atmospheres.
Okay, the next question is from Esteban. Why is there more matter in the universe than antimatter if the creation of matter from energy implies the creation of antimatter?
That's a great question, and it's a central question in cosmology because it has to be explained, basically. So let's start with the premise. So the question is a good one because, of course, it implies that it's a surprising outcome, that there's matter and no antimatter, or virtually none. So why should we be surprised? Why is this something we need to explain? Well, physics is extremely symmetric. It's not perfectly symmetric. There are extremely subtle asymmetries at the level of fundamental physics between matter and antimatter, but really they are almost non-existent. So if you have pure energy, you can create particles and antiparticles with equal facility. And in fact, that's how it happens. Pure energy can create, say, an electron and a positron, and though that particle and antiparticle can travel, the antiparticle, of course, will annihilate eventually with the particle and disappear. But energy is able to create particle-antiparticle pairs. This can occur where the particle and antiparticle get liberated into the universe to further interact, or it even happens in what's called a virtual sense, where there's an evanescent or almost transient situation where the particle-antiparticle pairs appear, and before they can even emerge out of the vacuum, they disappear again. This is a quantum effect that's been measured in the lab. So nature, from energy, which is available abundantly in an expanding universe, can create particles and antiparticles in equal number. And in the early universe, in the Big Bang, where the energy was phenomenal and the temperature was phenomenal, we know that particles and antiparticles were being created continuously and all the time by the radiation. And it was a dynamic situation where there were equal numbers of particles and antiparticles coming in and out of being with energy. And of course, the energy was always there too, the extremely high energy photons. So that was a completely symmetric situation. But if we look at the universe now, when it's old and cold and huge, antimatter is hard to find. It can be created in a transient way from pure energy in a lab or in a particle accelerator. But the limits on antimatter in the universe are extremely stringent. And it's simple. Even though the vacuum of space is a pretty good vacuum, it's not a perfect vacuum. The space between stars, for instance, has about 1 or a fraction of an atom per cubic meter. So that's an incredibly good vacuum, billion times better than the air you're breathing, or the best vacuum machine on Earth. But that's sufficient that if there were pockets of matter and pockets of antimatter in the Milky Way galaxy, the interfaces between them would lead to gamma rays. Anywhere the particles and antiparticles come into a connection with each other, say protons or antiprotons or electrons or positrons, you'll see gamma rays. And we have very sensitive gamma ray telescopes. We've had them in space. And we've done full surveys of the sky with them. So there are no places in the universe where antimatter comes into contact with matter. And so we know the universe is made, the Milky Way is made of matter. You can extend the argument to galaxies in the extragalactic universe. Even though the space between galaxies is an even better vacuum, probably 1,000 times better vacuum than the space between stars within a galaxy, it's again not a perfect vacuum. Galaxies interact, they come into contact with each other, and there's a very diffuse plasma in the region between galaxies. So if there were galaxies and anti-galaxies, or the spaces between galaxies had pockets of matter and antimatter, once again they would come into contact, even though the densities are low, and the gamma ray telescopes are sensitive enough to see the annihilation radiation that would result. So basically for 25 or 30 years, since the first sensitive gamma ray telescopes, we've known that there is no antimatter in the universe. It can only be created in this fleeting way. The universe is overwhelmingly one of these two flavors of stuff, not the anti-stuff. And so it is something to explain. So you have an early situation in the extremely early universe where antimatter and matter are created equally out of pure energy, and you have a situation now, billions of years later, where there's no antimatter, it's just matter. And the other thing that's on the table in this is that for every particle in the universe, i.e. electron, proton, neutron, which in turn, of course, are made of quarks, there are about a few 100 million photons, the very low energy photons left over from the Big Bang, the microwave background radiation. So we have another thing to explain in cosmology, which is why are there so many photons per particle? And so all these pieces of information come together in an explanation where a slight asymmetry in the forces of nature led to antimatter being created with slightly less proclivity than matter. That asymmetry was, a few parts in a billion, basically. So very subtle asymmetry in the forces of nature out of the unification of those forces in the early universe. That asymmetry led to this tiny excess of matter over antimatter, and in the early universe, in the first fractions of a second, when the particles and antiparticles that were created in abundance from radiation disappeared for the last time in all their interactions, then the photons were left over to fill the universe as it expanded and cooled, and the tiny little residue, that excess of particles, became the matter content of the universe. So conceptually, you can imagine something like 1,000,000,001 particles for every billion antiparticle. And those billion particles and antiparticles annihilate to create a billion photons, and the one particle is left over. So you end up with an old, cold universe where that one particle, each particle is now outnumbered by those low energy photons, the microwave background. So that in a schematic way is the explanation. The details of it, of course, depend on the unification theory for the forces of nature, and that has not yet been confirmed by experiment. So it is somewhat speculative, the explanation, but that's roughly how it goes.
Okay, the next question is from Gail. In your book, The Living Cosmos, in the section on Europa, you pose this question: what if life is so strange that we can't recognize it? You think there is the possibility of a strange kind of life existing on a moon like Europa? And how could we devise ways of detecting such life forms?
So it's a good question about life as we don't know it. Life in a different form. Actually, I guess, having thought about it more, I would imagine Europan life, if it exists, it might not be that dissimilar to terrestrial life, because Europa does have an ocean. It's likely to be a salty ocean, which may not have the same pH as Earth's oceans, but it's going to be chemically fairly similar to the Earth's oceans. It's, of course, it's a frigid biosphere. There's tepid heating from geological activity within Europa, which is a moderately large moon of Jupiter, but nothing like the heat that Earth has with its hydrothermal vents under the ocean and its sunlight on the surface. So life on Europa will be strange. It will be unusual just because it's a frigid environment and the metabolism would have to be quite different. But the basic biochemistry may be the same. So Europa may not be the place where life is really weird, if life exists, because it's formed in a liquid environment that's similar to what happened on the Earth 4 billion years ago. I would actually pick as a better example than they maybe did in that book, Titan, if you want life as we don't know it, if you want really weird life. Because if biology is possible in a medium consisting of ethane, methane, and a little water and a little ammonia, then it's going to look completely different from the Earth. Its biochemical basis will be different. Now, I guess it doesn't necessarily follow that if the biochemical basis is different, the organism that results from that biochemistry will be different. But it's a fairly good bet. If the basic building blocks and ingredients are different, it's very hard to imagine how the ending of life form would not look different as well. So I would put a better bet on Titan as having a really weird life. And if Europa has life, I'd probably put a mild bet on it being somewhat similar to terrestrial life, microbial, perhaps, fish, jellyfish, snails, who knows, sea urchins. I don't imagine the same species. I'm just being facetious there. It's a huge question, and people are basically just speculating, because with one biological experiment in the universe to study so far, the one right here on this planet, we can't use induction. The scientific method essentially fails us. And so it's a evidence-based subject, astronomy. You have to go out and find the evidence, and I suspect we'll be surprised by whatever we find.
Next question is from Chris. Given special relativity and the fact that radio waves move at the speed of light, does time dilation have the same effect on RF as it does visible light? How would time dilation affect radio transmissions between ships traveling at velocities near the speed of light, between ships and planets or orbital stations?
That's right. It's exactly the same. It's the same mechanism. Special relativity. The equations are sort of agnostic to the wavelength or the frequency of the radiation. If it's any form of electromagnetic radiation, the way the time domain is affected goes as the same way based on the velocity of the source of radiation relative to the speed of light. So yes, radio waves would be affected, radio signals would be affected exactly analogously to the way optical signals are affected, or gamma rays, or any other radiation you care to mention.
Okay, David is interested in solar systems. The first is what determines the speed of planetary orbits, and then kind of related is how are two-star systems formed, binary star systems formed.
So the orbits of objects in solar systems, planets or other smaller pieces of debris, they're governed by Kepler's law, and that's Kepler's laws, which of course give a mathematical relationship. They give the orbital speed as a function of distance from the central source. And these equations are approximations in the situation where the mass of the planet is much smaller than the mass of the star that's orbiting, which is true, for instance, in the solar system, Jupiter being 1,000 times less massive than the Sun, and all the other planets much less than that. So the mass is really dominated by the central star. And so Kepler's laws describe very well these orbital situations. They describe the variation in speed of a given object in an elliptical orbit, or they describe the relationship between the orbital speeds of different objects in the system as you move out from the central star. And Kepler's laws are, of course, a reflection of Newton's law of gravity. That's a simple calculation exercise that undergraduate astronomy majors get to do, of going from Kepler's laws to Newton's law of gravity. The binary star system is an interesting one. That's a system you can conceptually just imagine a situation where the mass of the planet is very large and eventually rivaling the mass of the star. So now you have two roughly similar massed objects orbiting each other, and of course they will co-orbit a common center of mass. Their orbits are still described by Newton's law of gravity, of course, for two objects, and the binary star orbits are very predictable, and they're very repeatable, and so when astronomers study binary stars, they know exactly what they're going to find. Now, to complicate things, either or both of those stars in a binary system might have planets around them, and those planets will tug on the parent stars. And one of the interesting pieces of exoplanet research is the awareness that since most stars are binaries, the Sun is actually slightly unusual because the simple majority of stars are in binary or multiple systems. It becomes of great interest whether binary stars and multiple stars have planets with the same incidence as normal single stars. And the research suggests that they will, because most binary stars are in fairly wide orbits, well beyond, for instance, the distance between those two stars being substantially more than the distance to Jupiter or Saturn. And in those kind of systems, terrestrial planets on tight orbits like the Earth or Mars or Venus would not actually be impacted by the binary star. The binary star is just doing a big enough co-orbit that interior planets are not perturbed, affected, or tossed out. So we can anticipate that the planetary systems will be found in binary stars. And then, in fact, Kepler has found a couple of very prominent examples. They're called Tatooine planets because they are situations where, as in the Star Wars movie, a denizen on one of those hopefully habitable planets would witness double star sunrises and sunsets.
Okay, the next question is from someone who's in our live session now. Abhinav. When a massive star dies, one possibility is that it may form a black hole. In those last moments, the delicate balance between the gravitational force and nuclear force breaks down and the star collapses on itself to form a singularity. What exactly is the singularity?
Yeah, so you've hit on the part of the theory where we actually don't have a good physical description. The process of forming a black hole involves, as you suggest, the situation where the pressure support from nuclear reactions is lost for the last time because you've reached the most stable element, iron, and once iron is reached, it takes energy. You have to put energy into the reaction to get energy out, and so in that situation, the iron core will collapse, and it'll collapse in essentially a gravitational free fall. So it's an extremely rapid compression of the center of the star. And logically, well, two things happen. In the models done in supercomputers, and it was also modeled out of pure gravity theory, the compression bounces. So you have a rapid collapse followed by a bounce, and that bounce creates a blast wave. That's really what a supernova is. It's an almost instantaneous heating up of the expanding gas to temperature of billions of Kelvin, where heavy elements are made, and the thing lights up in X-rays or gamma rays, and then continues on out for decades, centuries, millennia. You can see it in the sky. Meanwhile, that collapse, that free fall itself, has put enough of the material from the massive star into a region that's smaller than the Schwarzschild radius, that formally it meets the definition of a black hole. So the gravitational collapse has created something that is dense enough that it meets the definition of a black hole, which is to say a density such that there's a region where the escape velocity is the speed of light. That is what the event horizon is. It's a formal definition. It's not a physical surface or a barrier. It's just a mathematical definition. So the black hole is created. The singularity is another part of the black hole theory, because when you make a model of black holes using general relativity, there's a serious problem. The serious problem is that in predicting the interior properties of the black hole within the event horizon, simple general relativity theory predicts a singularity. In other words, predicts a cusp of density at the center where it becomes infinite. The mass density is infinite. And that's the formal definition of a singularity. And relativists have known for a long time that that's not physical. That means that it essentially points to a flaw in the theory. Any theory that describes an infinity that drops out of a calculation is essentially recognizing a limitation in the theory. And that's what Stephen Hawking meant when some decades ago he famously said, black holes contain the seeds of their own demise. He didn't mean that the black holes have a way of dying as black holes. He just meant that the theory is not fully descriptive of what goes on inside the event horizon, because it predicts a singularity which is unphysical. So that's a sign that black hole theory is not complete, which is why it's a very active field of theoretical research.
Next question is from John. Why are the subplanet rocky objects concentrated in the asteroid belt and beyond Neptune rather than being more uniformly distributed around the solar system?
That's a good question, and that hasn't come up before, but it's a good question. Why are things the way they are and distributed the way they are, especially the small rocky debris? The basic answer is that when the planets form, they essentially sweep out zones in the solar nebula. So the solar nebula, the rotating disk of gas and dust with the infant sun at the center, forms through a process of accretion. Rocky objects, initially planetesimals, things that are hundreds of kilometers across or asteroid size, and then gradually, by gravity and accretion, those sweep into rocky objects that are the size of Earth or terrestrial planets. In the outer solar system, those rocky cores that are terrestrial planet size gradually accrete mantles of hydrogen and helium and become gas giants. So the simplest way of explaining the asteroid belt is that it's a failed planet. If you sweep up all the mass of the asteroids, which of course exist over a quite large range in radius, they're not in a very skinny band at all, they're really quite spread out. If you swept up all that material, it's about 4% of the mass of the Earth. So it doesn't really amount to a full rocky planet, even anything like Mercury or Pluto. So what does that mean? What's the explanation? The best explanation is that that was a zone of material that might have been headed towards forming a planet, but it didn't have the critical mass, and there was never, the process of accretion was inefficient enough that it never formed a strong rocky core that could pull all the other material onto it. So it basically stayed as this rocky rubble. And then over time, remember 4.5 billion years have passed since then, the rocky material, because it's not accreting and forming a planet, when they collide, those pieces are going to gradually scatter. And so some of the pieces will scatter inward, and some will scatter outward, and some, of course, will scatter up and down and leave the system. But it's going to gradually spread out this band of material and then remove all possibility that it can gather together to form a planet. So we're now just seeing the sort of last residue of this failed terrestrial planet at the distance of the asteroid belt. And the Kuiper belt is a similar situation. The Kuiper belt does extend over a fairly large range of distances from the sun. It's like roughly 40 to 80 astronomical units. That's a huge hard piece of real estate. And there it's even easier to see why it would fail to form a large planet, something the size of Uranus or Neptune, because the diffuseness of the material at those large distances means there just wasn't enough to gather together to form a planet. And so it also has stayed as rubble. And at the outer edge of that, the outer edge of the Kuiper belt, you're pretty much seeing the edge of the solar nebula, so that 80 to 100 astronomical units out. That was essentially the full extent of the disk that formed all the planets. And that's the edge of the whole system, basically.
Another couple solar system related questions from Helmut asks, what would happen if you removed an outer planet from the solar system? How long would it take for the other orbits to change? Like days, years, millions of years? Would Earth still be habitable?
So these, the hypothetical of changing the solar system is an interesting hypothetical, and of course it was always hypothetical in the past, and you could do a theoretical calculation. Now we can do it with simulations and computers, so it's actually easy to do these thought experiments in a computer and see what would happen. If you remove actually one of the giant planets, say, pretty much any of them, you will not profoundly affect the solar system, but over long periods of time, which is to say hundreds of millions of years or even billions of years, there will be different resonances. So we know that the solar system has changed its architecture over this long span of time, 4.5 billion years, due to resonances between the large objects, the giant planets in particular. The resonance happens when the orbital periods of any two large planets, the ratio is a ratio of whole numbers, 1 to 2, 3 to 2, 5 to 4, it doesn't matter, any ratio of whole numbers. That will create a resonance state where a sequential kick, mild kick is applied that moves the orbit potentially out of a stable orbit and then rearranges the whole system. So if you remove one of the planets, you create a new potential for resonances, which you change the gravitational situation. But the resonances are fairly rare. So when you play forward models of the solar system, if you remove a planet, not much is going to happen. I mean, these resonances might occur, but you're going to probably have to wait billions of years before resonance happens that causes a rearrangement. Another more interesting hypothetical, which people can also do with computers, rather than take away a planet, what if you add a planet? And if you add a planet, the result is very interesting and it's more dramatic. The best way the dynamicists would put it is the solar system is full, completely full. So we know in our little scale models, so we talked about them in the class, how incredibly empty the solar system is. It's got these 4 rocky terrestrial planets and 4 gas giants, but they're tiny compared to the distance between them. So the entire disk of the circular orbits in the solar system is essentially empty space, 99.69, probably 15.9% empty space. But because gravity has an infinite reach, the effect of adding something is quite dramatic over time. And if you drop just a modest-sized planet, something like a Mars, into either the inner solar system or even the outer solar system, just say you drop Mars, something like Mars, between Jupiter and Saturn, just halfway between Jupiter and Saturn, just let it orbit and see what happens. The result of that in simulations is that in a much shorter than billions of year timescale, probably a tens of millions of year timescale, which of course is still many hundreds of thousands of orbits, so it's time for things to happen by accumulation, you will rearrange things. You will eject things. If you drop a Mars into the inner solar system, just try and make the inner solar system richer than it is, you pretty much eject something, or maybe even eject more than one terrestrial planet. If you drop it into the outer solar system, the same thing can happen. Either that new object is ejected itself, or it causes the giant planets to rearrange their orbits such that one of them ejects another one of them. So, and these are quite profound effects. So in these hypotheticals, adding something, even a small thing, is actually much more profound than taking something away. But they all have some effect over a long time.
Okay, and in a related question, what would happen if the moon were to disappear or be destroyed by an asteroid or meteor?
So the moon is important for us because the moon stabilizes our orbit. Now, some people have, the moon, of course, we think was formed from the Earth, so it's really part of us anyway. It was formed by an impact of a Mars-like object onto the Earth probably 50 million years after formation, because we can age date the difference between the moon from Apollo moon rocks and the oldest Earth rocks, and we can see that difference. So we know the moon is very slightly younger than the Earth, so we know when this event probably happened. Maybe because the moon is such a large moon relative to the planet size, it has a very strong effect on the Earth, and then what it does is it acts to stabilize the orbital tilt of the Earth, which is what causes the seasons. In the absence of having a moon, the Earth's orbital tilt would vary over a much wider range over geological time. we see the example of this in Mars. Mars currently has almost the same orbital tilt as the Earth, 25 degrees instead of 23.5. But we know from geological records and sort of clever analysis that Mars's orbital tilt is varied between probably 20 degrees and 50 degrees over cosmic time, because as you know, Mars has two tiny little moons and they're not sufficient to stabilize its orbit. So by analogy, if the moon were to suddenly disappear by being destroyed by an impact or whatever, that's pretty much the only way it would happen naturally, that will have a profound effect on the Earth. The most obvious of which is that the Earth's orbital tilt would start varying, not from year to year or even millennium to millennium, but over a significant time beyond that. And so the seasons on the Earth and the climatic variations on the Earth would be quite dramatic. Of course, the other effect of losing the moon would be you would lose the tidal effect of the moon. So the ocean tides and the land tides that also happen would disappear. Now, what difference would that make? There's speculation that ocean tides were relevant in terms of the formation of life, as was the stabilization of the Earth's orbital tilt, therefore reducing the climatic variations, making it more temperate, if you like, and continuously temperate for life. So, if the Earth's already inhabited by microbes, I don't think the loss of the moon would eradicate life on Earth, but it would make life on Earth, it would make a tougher proposition for life on Earth.
Okay. Franjal would like to know what is beyond the electromagnetic spectrum. Like, for example, what lies at higher frequencies than gamma rays or lower frequencies than radio waves?
That's a good question. I've not had that question before. In principle, the electromagnetic spectrum, is not bounded. Conceptually, it's not bounded at all. If you had the ability to create these waves, that they could exist. So what are the natural bounds? I mean, what in astronomy and the natural physical universe do we see as the bounds on this kind of radiation? And that is a good question. So at the low end, the low energy end, the longest waves that we can harness and work with radio technology and telescopes are meter length waves, radio waves that are a few meters long, which is incredibly long wavelength for incredibly low energy for radio waves. So those radio waves can be detected from the universe. They obviously are created naturally and astrophysically, and we have technology to work with those waves. But those are not the longest waves that could exist. I'll give you the physical example of where even longer radiation will eventually exist. As the universe continues to expand at an accelerating rate due to dark energy, the microwaves left over from the Big Bang will of course stretch with space-time and accelerating expansion. And conceptually and theoretically, those waves will just eventually expand way, way beyond the meter-length radio waves that we can harness and measure in the universe to an incredibly large length. So in physical cosmology, we have the notion that in the far future of the universe will be filled with incredibly low energy and incredibly long wavelength electromagnetic radiation. That's just a logical continuation and extrapolation of what's happening right now. So that would be the extreme form of low energy radiation, essentially continuing forever. At the high energy end, it's also interesting. The natural limit on the highest energy radiation we can see, it comes from there's a physical limit, because when you're looking out in the universe towards extremely high energy gamma rays, you can reach a situation where in traveling through even intergalactic space, which is, we know is not a pure vacuum, but has some low level of ambient plasma, protons and electrons, these gamma rays will actually create pairs, annihilation pairs, and will be absorbed. So when you get to very high energy gamma rays, you get to a situation where the gamma rays are quenched just by traveling through the universe itself. And so we won't see gamma rays beyond a certain energy level. Now it's very hard for telescopes and astronomy to work at that very, very high energy level. It has to be done from space, of course, because the atmosphere is opaque to gamma rays. But in principle, there's an upper bound on the gamma rays, not that can be created in the universe by astrophysics somehow. Maybe at the edge of a black hole, there's enough energy to make extraordinarily high energy gamma rays, but they will not travel through space because of this quenching process.
Right. A lot of people are interested in the Dawn mission and Ceres, and would like you to talk about that. What is the latest with that? What's the relevance of the mission? And then do you have any speculation as to what the bright spots might be that have been seen?
Yeah, Dawn is now in orbit around Ceres. It's another fantastic success in the space program working in the outer reaches of the solar system. We just had the Rosetta mission, which it had some failures. It was not an unalloyed success, the Rosetta mission, but we did learn a lot about that cometary surface, and the data is still being digested. With Ceres, the largest asteroid discovered in 1,000 kilometers across, discovered in 1800 in Chiazzi, I think it was, in Italy, if I'm getting my history right. That's an interesting object because asteroids have not been considered that interesting. I mean, they're considered just lumps of rock, sort of baked dry over time, possibly with some modest amount of water held deep inside, but not really very interesting, essentially arid, dead rocks. Ceres is large enough that the first interesting aspect of Ceres is that it's at that just beyond the level at which a rock turns round because of the action of gravity, especially when it's forming and it's still molten or tacky. If it's big enough, then gravity will form a round symmetric object. Notice the two moons of Mars, Phobos and Deimos, are below that level, and so they are potato-shaped. They will not made round, and smaller asteroids will not be round either. So Ceres is large enough to be round, and really the round objects in the solar system are planets and dwarf planets and very large moons, so they're all interesting to us. And so Ceres joins that category. Just seeing it as round tells us it's interesting because its gravity is actually quite strong. Going along with that strong gravity is the possibility of activity, which means that it doesn't have to be a dead rock. It's got sufficient gravity to make itself round. It's got sufficient gravity to have internal heating. It's got sufficient mass to have radioactive heating, just due to ambient radioactivity in the rocky material. And so the surprise and the discovery as Dawn approached Ceres were that these twin hotspots, white areas, very prominent areas, that came into sharper and sharper focus as the spacecraft approached them. They were just big blurry dots originally. Now they've been separated, resolved, and we can see that they're actually very small. And the speculation at the moment is that Ceres has going on inside it something called cryovolcanism. It's not a truly volcanic planet the way Earth and Venus and Mars in its past were, with true volcanoes on its surface. We do not see volcanoes on the surface of Ceres. It has no atmosphere, so we can see the full surface and no volcanoes there. But there's a more subtle form of volcanism that can be caused by mild geological activity just from this natural heating of the ambient material. And that can drive activity. It can potentially turn parts of the interior of Ceres into magma, maybe not, full-on volcanoes spewing lava out onto the surface, but tacky, convective, circulating, semi-molten rock. And that energy, of course, if there's liquid water trapped in the rocky material, can drive that liquid water out of the rocky material, and that's what we think is happening with these hotspots. These hotspots are most likely to be water and other sort of chemicals. It's not just pure water; it's sort of minerals dissolved in the water, and so those white stains, if you like, on the surface of Ceres are sort of chemical stains precipitated out from material that would be dissolved in water. But there's undoubtedly water in Ceres. It's almost the only way we can explain those hotspots. So there's some very mild form of volcanism, cryovolcanism. There's almost certainly a layer underneath Ceres where there's magma and where there's some form of liquid water mixed with rock. And the activity, the energy, can drive that water out and other minerals and create these hotspots. So it's very exciting because that's a lot, for something that we thought might just be a dead rock. That's quite a lot of interesting stuff going on. We're just beginning to learn about it.
Okay, the next question is from Alexander. How do scientists plan to use the Planetary Atmosphere's Minor Species Sensor, or PAMS, after tests in Tucson, Arizona? And how does the technology of intracavity laser absorption spectrometry work?
Wow, that's a very high-level question, and I can't fully answer it, to be honest. It's not a mission I'm completely familiar with. But there is the question of using tuned instruments to detect absorption is a technique that astronomy has pursued for a number of decades now. So you can use tunable lasers or masers even. You can form cavities, microwave cavities or laser cavities, and you can make resonant absorptions of various atmospheric species or chemical species or molecular species. So this sort of tunable form of detecting transitions due to molecules is very powerful and it's very sensitive. It's sort of a little bit like tuning a radio dial and just picking up a signal that way because you home in on the exact frequency where that signal exists. Well, you can tune in to detect molecules in an astrophysical situation with these technologies, and they're extremely sensitive. They can detect abundances of the relevant species that are, a few parts in a trillion, basically, so extraordinarily sensitive. You need a lot of radiation to do that, though. This cannot be done on really remote targets. It's most typically done with remote sensing in the solar system. People are trying to use versions of this technology, of course, to look at exoplanets, to look at stars and see what stars are made of. But you need phenomenal amounts of radiation and light to make this technology work.
Okay, a couple people have questions about wormholes. Wormholes have been postulated by science fiction writers for decades. What's the current theory on wormholes' existence, or is it possible to observe or create one? And will travel through them be possible?
So the theory of wormholes does emerge naturally from general relativity and curved spacetimes. It turns out, however, that our universe is a little dull as for the possibility of wormholes because the space-time we occupy, the large space-time of the universe itself, is almost completely flat. That is shown to us by measurements from WMAP and Planck, the microwave satellites that sort of measure the curvature of space on large scales and shown that space-time is flat. So there would be more possibilities of wormholes if we lived in a more convoluted space-time, where you could imagine the space-time interconnecting or connecting, and you can imagine almost these shortcuts through space-time because it was highly curved. Unfortunately, we don't have that situation. So if we have a black hole, that black hole is sitting in otherwise flat space-time. So while the theory might say that if space-time is convoluted, it could be interconnected, thereby offering portals between one region of space-time and another, which is essentially what a white hole would be, or wormhole. It would be an interconnection. The true space-time we inhabit doesn't seem to have that character. So what is inside a black hole? Well, there's the singularity that's already been alluded to in another question. And is there a possibility that inside the black hole, inside the event horizon, is a connection to a separate part of the universe, another part of the universe? It's possible in theory. So the concept of wormhole is valid within general relativity. It's just that our universe doesn't seem to be structured to make that a likely outcome. So most cosmologists and relativists are betting that the black holes that we have in our universe, because we've identified many of them, stellar mass and supermassive black holes in the center of galaxies, it doesn't seem likely that they connect to other regions of space-time. And so the wormhole remains hypothetical.
All right, the next question is from Henry. Henry says, I might be getting a Galileo scope. Is there a good website that I could use to keep up on upcoming astronomical events worthy of checking out using that Galileo scope?
Well, sure. The best single Galileo scopes are great. I'm hoping and I'm sure you got the tripod because they're really hard to use without a tripod unless you've got incredibly steady hands because they're pretty long focal length and small field of view. But they are great, and of course, can't beat the price. I think in all these things, the best website is still the one associated with the Sky and Telescope magazine, which is beloved with amateur astronomers, such circulation of like 200,000 copies a month sold. It's a good magazine, colorful, glossy, lots of reviews of telescopes, and it does a very good job, of course, every month of just laying out what's in the night sky, what's visible, what's not visible, and sometimes distinguishing what you can see with binoculars and what you can see with small telescopes. So their website is really nice, and so I just recommend Sky and Telescope website.
Right, so Gary has a question, and I'll try and simplify it a little bit. But he's interested in the Hubble diagram, and he wants to understand why it's not just as valid to convert the entire x-axis from distance in light years to time in years. Wouldn't you reach a different conclusion?
It's completely valid because it's look-back time. So the distance in light years in a Hubble diagram or any diagram in cosmology where you're representing distance, the distance is, first of all, let's just back off to how distance is measured in astrogalactic astronomy. Distance is measured through, sort of trite way, by a distance indicator. You have to have some characteristic of a galaxy or a distant object where you think you know what its true size is or what its true brightness is, and then you see what its apparent size or its apparent brightness is through a telescope, and you just use simple geometry of how radiation travels through space or the curvature of space to say what the intrinsic or true brightness or size of that object is, and that gives you the distance. So we do infer distances for astronomical objects, including galaxies, and we can plot those distances in the Hubble diagram. But you're right, the distance is completely and trivially convertible into a look-back time based on the light traveling through the universe or for that distance. And so that's a completely valid way of doing it. So as you move out in a Hubble diagram, you are, of course, looking back in time. And that's why when the Hubble diagram was first used by Hubble, he was looking at the very nearby universe. He only made his measurements within a few million light years. I mean, really, the very nearby universe, a few dozen galaxies was all. But by the 1970s, people were making Hubble diagrams for galaxies that had distances of hundreds of millions of light years, or even a few billion light years. And that was where cosmology got interesting, because that distance corresponds to a significant look-back time. And because the Big Bang model suggested that the universe should have slowed down as it expanded, people started to look for curvature in the Hubble diagram. Because if you acknowledge that those more distant galaxies are seen as they were in the past, they should have been moving apart from each other faster in the past than they are now, if the universe has been decelerating or slowing down. So the phenomenon you're alluding to, the fact that it's really time, or can be converted to look-back time, was critical because it led to this important idea in cosmology that by looking out in space and doing a Hubble diagram, you could measure this decelerating expansion and therefore affirm a key aspect of the Big Bang model. Of course, what will happen in the 1990s that shocked everyone was that instead of finding deceleration, people looking back in time found that the universe now was expanding faster than it was in the past. So the universe was accelerating. So they did find curvature in the Hubble diagram, but it went in the wrong direction. And that was an incredible discovery of 1995.
All right, Katerina is interested in Earth orbiting satellites and probes we send to other planets. We are always hearing about sending satellites, observatories, probes, to the far universe or on the Moon, Mars, and other planets. But I was wondering what happens when they stop working. Do space agencies have they worked out any way of retrieving old instruments or repairing them, disposing of them properly?
That's a good question. Yeah, what is it just space junk? And I think, unfortunately, for the most part, it is space junk. There have been a couple of well-known incidents where, in the case of an Earth orbiting satellite, where it is possible to fix it, we fixed a couple of satellites. Obviously, the most prominent is not a satellite; it's the Hubble Space Telescope, which was serviced 5 times. That's the last of those has happened now. And then there are a couple of prominent satellites that, because they cost hundreds of millions of dollars, it was worth sending up a robotic probe, or not in this case astronauts, to try and fix it. Or just using clever techniques from the ground to try and control, by electrical or electronic signals, the interior circuitry and the interior control systems of the satellite and rejuvenate it. Those methods sometimes fail, and they occasionally work, and they're incredible victories if they do work. However, many satellites just have a natural lifetime, either because their energy source will die. That could be because they're based on a radioactive energy source that just has a finite lifetime, or because they're powered by solar panels that degrade or decay over time, and they eventually just don't have enough energy to power themselves, or because their circuitry or components die. And typically, for Earth orbiting satellites or space missions, the death of the electronics is caused by cosmic rays or micrometeor impacts. It's a pretty harsh environment for space. Space electronics is rated quite differently from any other kind of electronics. The circuitry and the integrated circuits in the space satellite are quite different from the ones in your smartphone. They're battle hardened, essentially. They're rated to handle huge doses of cosmic rays and radiation. The military spec, basically. They take a military spec and then they sometimes make it even beyond that. So I would say, I'm trying to put a summary on that. I would say, in terms of Earth orbiting satellites, 90% of them or 95% of them, when they die, they're just dead. They're just junk up in space, and we have a growing amount of junk up in space. Satellites that have finished their lifetimes. Sometimes they degrade their orbits and fall into the ocean or burn up in the atmosphere, and so they're sort of taken out of circulation that way. But in large part, they just sit there orbiting and accumulating as space junk. And a lot of our space missions into the solar system are in the same domain. Mars is not littered with, but has a steadily growing number of rovers and space missions that are just sitting on its surface inactive and will never gather any more data. So that's sort of the fate of most space missions, I think.
Right, we still have a lot of interest in dark matter and gravitational lensing, and in particular, there was a recent discovery of a supernova that we've been seeing over and over and over again. And they're wondering if you can talk a little bit about that and about dark matter. And yeah, that's it.
So the lensing, just to give the general view on this, gravitational lensing is a prediction out of general relativity. It was made right when the theory was published in 1916. It was considered unobservable for decades, actually. And then some more formalism on lensing was put in place by Refstal, a Belgian astronomer and theorist, in the 1960s. And then finally, in the 1970s, lensing was first observed. So the principle is just that gravity bends light, and you can have a situation where there's an object between you and a more distant object, and that an intervening object bends the light of a more distant object, just like a lens would, just a direct analogy of an optical lens. And just like an optical lens, that gravitational lens, a mass lens, can magnify, distort, or occasionally demagnify the light of the background object. And that effect was first detected with quasars and galaxies in the 1970s. It's been seen hundreds of times now, probably thousands of times. So it's a routine thing. Why is it valuable? And that connects, well, it's as apart from an affirmation of general relativity, that's its first thing you can say about it. General relativity has been affirmed hundreds or thousands of times by all these observations of lensing, each a little gravitational optic experiment that agrees with Einstein's predictions. That's great. The second thing relates to dark matter, which is the other part of the question. We're having real trouble understanding dark matter. The dark matter candidate particle has not yet been observed in an accelerator or physics lab, so astronomers are left trying to understand dark matter as best they can. And the best way to understand dark matter is in these little gravitational optics type experiments, because when matter bends light, it doesn't matter whether the matter is visible and glowing or dark and invisible and very weakly interacting. So when you look at one of these gravitational lensing situations, you can weigh the intervening object, the lensing object, completely. You can weigh its visible stuff and its dark stuff. So our best measurements, our best inventories or censuses of dark matter are coming from these little gravitational lens experiments. And it's these experiments that have told us that dark matter exists everywhere in the universe, on scales of dwarf galaxies, massive galaxies, even between galaxies in the voids of intergalactic space. So lensing has been critical in showing us that the universe is indeed made of dark matter, roughly six times as much as all the visible material, that dark matter is widely distributed, but it does clump because dark matter is a particle, we think, weakly interacting with electromagnetic radiation, but it has gravity, and so it will clump and cluster over time, just like normal matter will. And our mapping of dark matter has been the best and most exquisitely done with these lens experiments. So it's taught us a lot about dark matter. Unfortunately, it hasn't answered the question of what dark matter actually is. I think there was another part of that question that I didn't get to. Matthew?
Sorry, Chris. Oh, which? Sorry.
I think there was a part of that question I didn't get to, but.
Oh, it was just about the recent discovery of the supernova that we've been seeing repeatedly over and over and over again.
That's good. I'm glad that was asked. That's a beautiful picture. So, what can happen in a lensing situation is that the light can take different paths in the lensing. It can travel a longer distance and be bent a lot, or it can travel a shorter geometric distance and be bent less. And that means from a single source, the light travel time of the different paths can be very different. And it can be different by centuries or millennia, or just a few years or a few months, depending on the geometry. And in this wonderful case, where there's a supernova going off in a distant galaxy, the different paths that the light from that supernova take mean we can see that supernova at different stages after it went off. So you just essentially get multiple views of a supernova spread out over time, sampled over time, all displayed in one image because the light has taken different amounts of time to get to us. So we look back in time and see it at different snapshots in its history. So it's a kind of lucky situation to be able to see a dying star in a distant galaxy sampled at different times after its death. And it makes for a pretty spectacular image.
All right, we have one last question, and there are two people who have asked questions about neutrinos. Can you talk about what's going on in neutrino astronomy, and what's the impact of all the tiny neutrinos moving around in the universe?
Okay, I'll try and summarize briefly. It's a big subject, neutrino astronomy, and we're trying to do full-on neutrino astronomy. Neutrinos were detected from the sun in the 1970s, so neutrino astronomy did start existing then, but it's been very hard to detect neutrinos from other astronomical sources. But I think we're getting close to it now. So neutrinos are abundant particles in the universe. They should be roughly equal in abundance since they're just essentially a cousin of an electron as a light particle. So they should be equally abundant to protons, neutrons, and electrons in the universe. Now that's important because, since we've been talking about dark matter, if neutrinos had mass, and because they interact so weakly with matter, they fit the bill in principle for being dark matter. And so the interest in neutrinos in cosmology came immediately because we know there's a lot of neutrinos, because we know they don't interact with normal matter or electromagnetic radiation. So if they do have mass, it adds up to a lot, and they could be dark matter. Neutrinos, however, were ruled out as being dark matter because the mass limits on neutrinos do not allow them to be 6 times more massive in total than all the protons and neutrons in the universe. So neutrinos cannot be the dark matter or all of the dark matter. They can be a little piece of the dark matter. And as for what neutrino masses are, that's been a very difficult thing to determine. So as we speak, there are no mass measurements of neutrinos. In simple form of physical theory, because neutrinos travel essentially at the speed of light, they have no mass. But neutrino oscillations were first observed almost 20 years ago now, and that is a situation where in physics experiments, there are 3 possible flavors of neutrinos. Among the leptons or light particles in the scheme of particle physics, you have electrons, the familiar electrons that normal antimatter is made of. And then you have heavier versions of the electrons, a few hundred times heavier, called muons. And then you have even heavier cousins called tau particles. And in the scheme of particle physics, each of those has a neutrino. So there's an electron neutrino, a muon neutrino, and a tau neutrino. And they're all roughly equally abundant and should have different masses. People have been trying to measure neutrino mass for a long time, but what they did find was that neutrinos, as they travel through space at essentially the speed of light, can oscillate or change flavor between the light and the heavier versions. So even though we can't measure the mass of a neutrino, we can measure essentially the difference in the products of the masses when they oscillate from one form to another. So that's a fascinating hint from high energy physics that neutrinos do have mass, but you can't measure the mass of any one species. So it's going to take some ingenuity to figure that out. When the mass is understood of a given neutrino or a given flavor of neutrino, then we'll be able to plug them into the cosmological landscape and understand what effect they have on forming large-scale structure in the universe, even if they don't even if they don't form galaxies and keep them together by acting as the full dark matter.
That's the last question. Thank everybody for joining us. Thank you very much.
Yes, we'll be back next week. Goodbye, everyone.